This podcast is brought to you by the Albany Public Library main branch and the generosity of listeners like you. What is a podcast? God, Daddy, these people talk as much as you do. Razib Khan's Unsupervised Learning.
Thanks for listening to the ungated version of the Unsupervised Learning podcast. If you want to read some essays on some of these topics, please check out razib.substack.com. Again, that's razib.substack.com. Thank you.
If you have a sibling with autism, your future child's risk for an autism diagnosis is increased by a factor of 2 to 3.5. Orchid's whole genome embryo reports can help mitigate your child's risk by screening for over 200 genetic variants, definitively linked to autism and other neurodevelopmental disorders. Discuss your situation with a genetics expert. Hey everybody, this is Razib with the Unsupervised Learning Podcast, and today I am here with my friend Eliah Overbey, who is an assistant professor of bioastronautics at the University of Austin. And I'm talking to Eliah partly because she had a lot of papers that just came out as I'm recording this, within the last month. I saw it on social media. I'm seeing it on her Google Scholar page right now. And I want to talk about some of the work that she was involved in, which was a lot. But first of all, Eliah, can you just talk about what your academic specialty is? Because I don't think most people know that there's a field called bioastronautics.
Yeah. So bioastronautics, broadly speaking, is how we're going to take humans on Earth and make them live in or help them, assist them live in other places, whether that's low Earth orbit, whether that's the moon, whether that's Mars. It encompasses every single aspect of human health, the psychological factors, the physiological factors, and then my area of research, my specialty, the genomic factors.
Yeah, and I will dig into the genomic part because that's the stuff that I also know a little bit about, although not in a zero gravity context. I see some stuff about like transcription and whatnot. That makes sense, and we can talk about why that makes sense. But first, let me ask. I haven't kept track of the stuff about. First of all, we don't have space shuttles right now. When I was growing up, a little older than you, but there were space shuttles, and they were always up there doing funny things. Now I think we have the International Space Station that American astronauts go to. I don't know, they might, as of this recording, they might still be stranded because Boeing can't make planes. No, I'm joking. But, it's not something a lot of people think about anymore, but it was a big deal a while ago. Now we are thinking about, I think, going back to the moon in the 2030s, manned launch. And obviously, we both live in Austin, Texas. And that is where Elon Musk lives. And I don't think I need to say more to the audience. He has some ambitions about moon and the Mars. And there's all these arguments about the scientific feasibility of, say, for example, the Mars mission because of the radiation. And is it worth it? It seems so much more cost-effective just from a utility perspective to send unmanned, right? So there's all these things that I just threw at you. Aside from, bioastronautics and what you do right now, I am just kind of curious, where are we with what we understand in terms of how zero weight loss, for example, affects us? So I've heard of things about bone weakening, bone loss, and it takes them a long time to recover. Question: do they actually eventually recover, even if they're on the International Space Station or wherever for 6 months or something?
Yeah. So in terms of bone and muscle density loss, astronauts do work out for 1 to 2 hours a day on the space station to minimize that. And it doesn't completely eliminate the loss that they experience, but it does help. I think one of the biggest limiting factors really is that we haven't had astronauts up in space for very long durations of time. So the record for the astronaut that's been up there the longest, for a while, it was Scott Kelly, who NASA did the twin study on. It's been broken by another astronaut at this point, but it still hasn't been much longer than a year. So if we're talking about a Mars mission, and if you're planning for a return trip, you're thinking that mission's maybe about 2 years long. We've only really done half of that on the space station.
Okay. And Mars mission is obviously, we can't go to Venus for various reasons that anyone can go search on Wikipedia why.
Or thinking about it. Some people have proposed cities in the sky on Venus.
All right, have they been reading a little too much Golden Age science fiction? But the Mars mission seems kind of feasible because it's not it's not going to melt the spacesuit. But you could go further. There's all this like science fiction about people in the asteroid belt and whatnot. So I mean, my question is like, if we had like faster transportation, would that obviate some of the problems with, say, like radiation exposure that people always talk about? Is it just like the time of exposure, or are there just like other things, like even if we could do things faster, it would still be a problem in space?
Yeah, so the further away you move from Earth, the less of Earth's protective shielding you have. So the International Space Station, for example, still has a lot of that radiation protection that we're not going to have on the Moon or on Mars. So there's that question of distance from Earth, but then there is also the question of how much time you're spending in space. And there's going to be some variation from what's being emitted by the sun, what the galactic background radiation is at the time. So it won't necessarily always be consistent between missions for any specific period of time. But yeah, like the short answer to your question is yes, traveling faster would help significantly minimize those risks. But once you get to Mars, there's no magnetic shielding on Mars like there is on Earth. So when you're on Earth, you're protected. When you're on Mars, you won't be protected like you are on Earth. So people have proposed building underground cities to shield from radiation while you're on the surface of the planet to leverage that. There's also people who think maybe better material science research into what you're putting on the ship could, and then what structures you would build on the surface could play an increased role.
All right. I mean, so just your opinion as a scientist who thinks a little bit more, well, actually thinks a lot more about this than most people. Obviously, I think like I remember George W. Bush. I mean, we should have been to Mars by now. I mean, you know what I'm saying? George H.W. Bush. Sorry, the first. I remember when I was a little kid, he said that we were going to be to Mars by like 2020 and all this stuff. We're still not back to the moon. Obviously, there's stuff that's going on in space. We have the space station. Looks like the Chinese are a little interested in doing things. And obviously, SpaceX, Elon Musk is. I mean, even like I was joking a little bit. I shouldn't joke, but like Boeing's craft is not doing well, but it's triggering some competition, so there's some change here. But I do want to say, I'm just curious, is this going to be like, oh, we're going to get there in like 15 years, and 15 years from now we're still going to say we're going to get there in 15 years? Because that's my whole life.
Yeah, I think there's a shift happening. I think particularly with the advances we're seeing in Starship, I think that's going to be the most likely thing that actually gets us to Mars. Some people at NASA may disagree with me. There's definitely disagreement about what'll get us there first. I would put my money on Starship if I were a betting woman. So I think it's more achievable than it has been in the past. But it is really hard to pin down numbers for this. I think it's also going to depend on what our risk tolerance is. And that risk calculation varies too, whether you're talking about NASA or whether you're talking about a private company. And so, for example, when I'm looking at the health factors in my research, some people, there are certainly a line of research where people want to figure out as much about the human body and don't want to send anybody there until we know it's safe. But I don't think that's necessarily the right avenue to take. I think all the data that we're collecting is going to help humans in the long run, but I don't think it's a prerequisite for if people want to take these risks. There shouldn't be, a barrier because the research hasn't been done.
Yeah, I mean, people have to remember how risky exploration was in the past. I mean, most of Magellan's crew, almost like the vast majority of Magellan's crew, including Magellan, died, in their around the world. And this is a very common. I've seen. I think it's probably exaggerated, but I've seen estimates that the East India Company of the a lot of them were German, actually. They weren't even Dutch, but the Dutch East India Company, a lot of those sailors that went to make their fortune, there was like as much as 90% of them might not have returned. Now some of them might have intermarried with the locals, but a lot of them just died. They died of disease. They died in pirates, like warfare, whatever. Exploration has always been a high risk, but humans used to have a much higher mortality risk tolerance, because mortality was death was a much more ubiquitous feature of our lives. Like right now, though, we are on the internet, in the metaverse, whatever we want to do. talking to AI, going out there is, I think, a little scary and weird to think about for some people. But there's still some obviously others like Elon Musk who would love to do it, right?
Right. No, I think that's true. And I think space exploration will probably be led by the people who are willing to take those risks.
I mean, I have heard from people, uh, and this is just, it's a viewpoint, like, where they basically say, why would you even do that? Why would you even do that? Like, why would you? What's the point in going to space? Like, our planet is overpopulated, and it's crowded, and we have all these problems. Why would you want to go to space? Now, there are obviously like rejoinders, but that is a viewpoint that's out there. But it's a big world. It looks like some countries, aside from the United States, are going to try to do it. And I think once that happens, competition really, really spurs people.
Yeah. Yeah, I think anyone who thinks the Earth is overpopulated might just need to spend a bit of time outside of a big city for a while. Yeah, in terms like why would we go to space? There's a few reasons. I mean, there's the national security and defense reason. It's a lot easier to attack people from the top of a gravity well than it is to attack people at the top of a gravity well from the bottom of a gravity well. That there's some lines of thought that whoever sits atop the gravity well is the one who's going to have the most control. So there's a serious concern from a national defense perspective and national security perspective. There's the issue of economics. People are starting to make money in space. People are still figuring out exactly how these economies will work, but there's a new viewpoint in space that wasn't necessarily there, for example, during the Apollo program, where you're not just doing space anymore for it to be a camping trip. You're doing it to create sustainable industry that'll make you money over time. And then there's also the argument that, we're not going to be able to live on Earth forever. Whether it's just the natural lifespan of the Earth, which of course is a very long time away, but more imminent threats such as nuclear war or pandemics, do you really want all of your eggs in one basket? You need to have backup copies of the human race somewhere. Mars is the lowest hanging fruit for accomplishing that most rapidly.
Yeah. I mean, I think most listeners will know I'm totally on board. I think we need to think bigger, outside the box. I think the last when it comes to space, the last 30 or 40 years, we've kind of been retreating, thinking inside the box, and have narrowed our horizons. So I think it's time for a change with the passing of the generation. So we'll see how that goes. I do have to say, if you read, and I don't read that much fiction. It's been a long time, just like time. You know how it is. But if you read science fiction from the 1960s, as opposed to the stuff today, they were just I don't want to say triumphalist, but like they did have a vision that we were going to populate this whole solar system in a very concrete way that's not as evident in more recent science fiction, where they tend to put it much further in the future. It's like they're not seeing it happen in 2200 because in their own world, everybody was going to cyberspace and people are fat. I think it's like
that's interesting. I mean, there was definitely a pace of technology that was different for aerospace flight in that era. I mean, they went from like the Wright brothers to the Apollo program was that like 50 years. It was very short in the grand scheme of things, and now it's over 50 years now from the Apollo program. And the pace doesn't seem to be quite the same. So I can see why just maybe passively observing that sort of aerospace progress has discouraged people's imagination.
Yeah. Well, okay, and I'm gonna get into the genomic stuff, because like that's why we're here. But I do want to say, I remember at my job in 2017, I think it was the summer of 2017, and there was like a SpaceX, I think it was Dragon, I don't remember, but it was reusable, and it landed, and I remember we were all looking at each other, we're like, wait, this isn't CGI. Because we are just so conditioned to space being kind of like within certain lines of like, okay, the rocket goes up, it blows up, whatever. There's a space station there, there's a satellite there, and to actually see what has been written up or has been depicted in science fiction films, a vehicle going into the edge of space and then coming back down and then landing in that way, it really, I think, made us, at that office, reconsider what the limits of the possible were in the near future, because I think I had read what Dragon was going to do, but I had not really internalized deeply what these vehicles could do and how they will reimagine going up and back to space.
Right. Yeah. So you're talking about like the sort of automated landing system where you can watch the
Yeah,
rocket.
these reusable vehicles. I mean, it's just like, this is like a totally new thing. It's a synthesis of obviously computing, because like there's got to be like some sort of like system in there that's taking advantage of all of the computation we have that was not possible in the 1960s, right? And so this is like all next generation technology. So speaking of next generation technology, I'm interested in next generation sequencing. I don't know if we should be calling it next generation sequencing anymore because it was next generation in 2007, but whatever. Like,
Right.
sometimes words just stick. I think we're going to call that for a while. But anyways, so I'm in this genomic space, and there's sequencing of the genome. There's transcriptome sequencing, which is the RNA. Other things going on. There's the methylome. These are buzzwords that a lot of my listeners have heard over the time. Why is that relevant to space and being in space, and how does space change gene expression? I guess let me ask that, just softball.
How does space change gene expression? Yeah, there's two primary drivers there. There's the microgravity that you experience. So when you're in microgravity, fluid redistributes throughout your body. There's different pressure on different organ systems in your body. From mouse studies, we think this is affecting the blood-brain barrier in the head. You can't quite study that with humans because you can't. How are you going to get those tissues? But in mice studies, you can actually see disruptions in the blood-brain barrier, and you can see degeneration of cone and rod photoreceptors and the retina, because you now have increased fluid pressure against the brain and the back of the eyes. And there's some influence about this fluid redistribution throughout the entire body that's putting different pressures on different organ systems. So there's the microgravity aspect. There's also the radiation component, which will affect genome stability.
Actually, okay, so let me ask you about the radiation, because when it comes to genome stability, mutation, like radiation is like one of the things that we I've heard talked about, but it's kind of like this outside thing that just happens. Mutations just happen. So like the human mutation rate is like what, like 2 times 10 to the negative 8 or 1.8 times 10 to the negative 8 per nucleotide per generation, whatever. These are statistics that I just like kind of memorize and I just know, and they exist out there. I don't think too much about the mechanistic details of how the mutation happens, what kind of radiation is, what is the rate of radiation. So do you guys have a sense of how much more the mutation rate increases? Like, obviously, like, people haven't reproduced in space to my knowledge, so I'm talking about just somatic cell mutations, right?
Right. Yeah. So, most of the studies that we've done to date have originated from the International Space Station. There's some older work too from the shuttle missions, but we weren't collecting this sort of data back when the Apollo missions were happening. So we're very limited in really understanding the impact that we can anticipate radiation playing on the human body. I've talked to a lot of scientists about this, and there's not a real great consensus. It's anywhere from a total showstopper to the same risk profile as perhaps smoking would have on the human body. It's one of those things where we just need more data, and we need to figure out what platforms we're going to use to collect that data. Again, I don't think this should be, nobody should be canceling their Mars trip if they want to take the risk. But from a scientific perspective, and perhaps to really open up Mars colonies for, a wider group of people who don't have the same tolerance for risk, these are the sort of studies we'll need to do.
Yeah, now I'm kind of wondering, do you know, have there been studies of people who've been at the space station and then what the rate of, I don't know, like de novo mutation caused diseases are in their offspring, right? That would be kind of curious, actually, now that I think about it.
That would be, yeah, I don't know of anything substantial that's been found from the space station, which is good news. But from their offspring, that's an interesting question, because I know that was when Chernobyl happened. Something that was of particular concern was not just the people who were exposed, but their children over time, and whether or not, their children should basically, I think some of the recommendations were that the children should have children with people far away from Chernobyl. Like they shouldn't have, you don't want the compounding effect.
Okay. So the compounding between de novo mutations and recessives.
Yeah, exactly. And I don't think that sort of analysis has been done for space station astronauts.
Okay. Wait, so about how many, off the top of your head, and just like general sense, how many people have been astronauts actually? Do you know?
It's about 600. 600 total people have been to space, roughly. There's a good website called supercluster.com, I believe it's .com, that keeps track of every single person that's flown, what country they flew with, how many days they were in space. They have the most up-to-date tally.
Wow. So I'm seeing I'm just checking online, 350 NASA astronauts. It's like a big village. It's very, 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 very small. Very, very small number of humans. So
peak physical fitness.
Everyone is, we've seen like the trainings and everything like that, or like people have watched, the right stuff or whatever. And, all those people, they're check their oxygen. So, in the next generation or so, this should go up by orders of magnitude then. I mean, probably we're talking tens of thousands and so you're going to get larger sample sizes.
Yeah, so we're starting to get, just to build on that, more commercial crews. So there was the Inspiration 4 mission. Axiom's a company that's been sending private crews to the International Space Station. Blue Origin and Virgin Galactic have shorter flight durations at the moment, but they are sending regularly now crews into space as well.
Yeah, so it seems like in the next generation, we're going to have orders of magnitude increased. Can you talk about, I know one of the papers talked about this, the Inspiration 4 crew, SpaceX. Let's just talk about, what are you guys finding, if anything? I mean, some of the results look like they're almost like null results that you're talking about, where we don't know, or at least we don't have the statistical power. We don't have the sample sizes to detect a major difference. Tell us, what happens when you go into space. Again, I know the basic stuff about bones, but there's got to be other things going on.
Yeah, one of the major things that we look for, that we first noticed actually with the NASA twin study, is changes in telomere length in a certain subset of PBMC cells. So these are, your audience, I think, is perhaps a bit more well-versed in genomics than some of the groups I talk to. But just briefly, those are sort of like the shoelace caps on the end of your chromosomes. And what happens is, over time, as your cells divide, the telomeres get shorter and shorter. So it's typically used as a marker for aging. And Scott Kelly, and then this was followed up with some additional astronauts who were on the International Space Station, his telomeres in a certain subpopulation of his immune cells did get longer during spaceflight. And there was this question in the back of my mind: was this due to the microgravity and the radiation and these factors of spaceflight, or was this due perhaps to the exercise regimens that they have to very strictly follow when they're up there? Because high intensity interval training on Earth can also have some impact on telomere length. So what we saw with the Inspiration 4 crew, they were up there for 3 days. The Dragon capsule is kind of the size of a large camping tent. Nobody's really doing any sort of workout in that space over that duration of time when you're only there for 3 days. So we looked at the telomere length for that crew as well. And what we saw was, even over the course of 3 days, for these crew members, their telomere lengths, all of them trended upwards. For one crew member, the lengthening was actually statistically significant.
So that's pretty fast.
Yeah, it is pretty fast. That was only over the course of 3 days. Scott Kelly was there for a year. The other NASA astronauts that were studied were there for about 3 to 6 months. So this was kind of one of the more shocking observations that we had. And
wait,
one of those.
Really quickly, the stylized fact is having longer telomeres or whatever is good, right?
Generally, yes. It could also be there's some forms of cancer that protect telomeres and elongate telomeres. So,
Because I'm just wondering when Brian Johnson's going to go in space now. Joking, but
oh, yeah, that's the fountain of youth. That's the next phase of Blueprint right there.
weird guy floating in space. Like, I'm going to live forever. Just floating. I don't know.
Yeah, one of the other things we look for is cancer risk, right? Because we are concerned about that radiation. So we do what's called a clonal hematopoiesis assay, where we look at the PBMC population. Again, those are just some of the easiest cells to collect from people, so we study them quite thoroughly. So we look at the PBMC population, and we look at the number of mutations that we can detect in that population before flight. We look at it after flight, and then we follow it longitudinally as well. So we'll still continue. We collect samples from the crew 3 months post-flight is the last time point in our study, but we continue to collect for as long as they want to give us samples. And we continue to look for whether or not there are any mutations in their blood cell population overtaking, what their genome was at the beginning of the mission.
And so,
good news for the Inspiration 4 crew. We haven't found anything on that front, but that's the other side where if you are a longevity wonk, you may not be enthused about that.
Yeah, I mean, so far, and obviously, with your sample size, I mean, you can't even really do a real GWAS with all of those 600, So I think like over the course of your career, you're really anticipating increasing the statistical power where you could answer questions that require more subtle effects, correct?
Correct. Yeah. So the data that we have now is really useful for generating hypotheses. When we first started doing omics assays, and still, to an extent, it's a fishing expedition where we're seeing what's changing and trying to piece together what could happen during long duration spaceflight from what we observe. As we collect more data, even if it's only from one person, 4 people, a dozen people, we can start to develop more targeted hypotheses and then develop more sophisticated assays around that.
Okay, I mean, like, so you were talking about, I think you said something about mice. Like, what are we getting from animals?
Yeah, so the International Space Station is flown a variety of model organisms. They actually have a mouse facility up there that can hold a few dozen mice. And so from those, we actually get full tissues from them. So we'll get the liver, the kidneys, the heart. I've looked at retinal tissue previously. There's also brain tissue. And these are all being deposited and stored. NASA has a database for this called GeneLab. I think they recently renamed it the Open Science Data Repository because they've expanded beyond genomic data. So there's that for mice. They've studied C. elegans, Drosophila, Arabidopsis. So there's a variety of different, experiments now that have been on the International Space Station. The ISS is actually a national laboratory. I don't think everyone realizes this, but the US, there's an organization called CASIS, the Center for Advancement of Science in Space, and they manage the ISS as one of the United States' national labs.
ISS, International Space Station, though, but there's modules in there for other nations, correct?
Yeah, so half of it is run by the Russians, half of it's run by the US and our partners. So yeah, the Japanese have
Europeans and Japanese. Yeah. Okay. And so so you have the animals, you have the humans, you have got the plants. So you're looking at so the question that I have, like one of the papers, actually, like, so it's transcript omics analysis reveals molecular alterations underpinning spaceflight dermatology. You're not a first author on that, but I was just kind of curious. So just for the listener out there, obviously you have a sequence, you have a DNA sequence, but a lot of those genes are not expressed in all tissues at all times. So they're turned on in some tissues, they're turned on in some contexts, and they're often they're repressed in a lot of contexts, right? And so environmental inputs can affect, easiest example would be a burn, can affect how your genes are expressing themselves. And so this is why transcriptomics, which focuses on the RNA that's transcribed from the DNA, is interesting and useful. And often what they do in transcriptomics is, take like time courses and stuff like that and see how the gene expression changes over time or changing in reaction to some infection, these sorts of things. So what did that paper find? What are your results out of the gene expression work?
So we collected gene expression data from a few different cell types and sample types, and we ran a few different gene expression assays on them. So we did, for example, Oxford nanopore sequencing on RNA from the whole blood, and that enabled us to look at epitranscriptomic modifications. And then we did single cell sequencing on PBMC population, so we could tease apart the T cell expression from the B cells, from the monocytes, et cetera. We also did, to touch on the skin component, was we took skin biopsies from the crew a month before their flight and then the day after they returned. And we did spatially resolved transcriptomics on those. So using that, we were actually able to tease apart gene expression in different layers of the skin. So we had gene expression profiles from the outer epidermis, from the inner epidermis, the dermal tissue, and the vasculature tissue. And through that process, well, we were very interested in the skin biopsies from reports from Scott Kelly on his experience when he returned to Earth after his year in space. He had actually a horrible skin reaction that he talked about in his book, where his skin broke out in rashes. Just the pressure of his clothing on his body was causing inflammation and irritation. There was some, he recounts in his book, do I go to the emergency room and talk to the doctor there about this? And he decided not to, because the doctors, had never seen a patient who'd been in space for a year and wouldn't really have a specialized protocol for him to follow. So he just took, it was like ibuprofen or some over-the-counter medication, and went back to sleep. So after reading about this experience, we got these skin biopsies from the crew. What we were able to see, they were up there for much shorter than Scott Kelly was, but we did see inflammatory responses in different layers of the skin. And we could pick apart different inflammatory pathways based on which layer you're looking at. And then also, interestingly, in the epidermis of the skin, we saw UV-specific responses, most likely from the radiation exposure that we weren't seeing deeper in the skin.
Mm-hmm. Wait, so UV radiation, and also, why do I hear about or read about gamma radiation all the time? What is that?
Yeah, gamma radiation is a type of energetic radiation. So there's different types of radiation you could be hit with in space. Some of it is energy-based, some of it is particle-based, and those can have different molecular effects on the genome.
Well, so one thing that I'm thinking is, with this, so there's some types of biology where, you're testing a very small number of individuals. I mean, I know in some types of neuroscience, the sample sizes aren't that large because, I don't know, if you're studying rats, there's only so many rats, the cost, right? And how many slices of the brain are you going to get and all these things. And so you focus on, small sample sizes, try to get big effects. But then, when you have large sample sizes, you can see individual variation. And, one of the maxims in genetics is this is totally true, but, pretty much everything is heritable in some way, I'm going to ask you kind of a speculative question. Can you imagine a situation where, excuse me, certain people are just pre-adapted for space, where they don't show as much stress, or their body doesn't change as much? I don't know. Just I'm imagining what you can imagine in the future.
Yeah, that's possible. And I think we've had a lot more, it's been a lot easier to collect samples for genomic studies actually from commercial crews than from NASA astronauts. And I suspect this is because NASA astronauts might be worried that NASA will apply for exceptions to GINA, the Genetic Information Non-Discrimination Act. And so, NASA astronauts might be worried that if there's something in their genome that indicates they're more susceptible to radiation damage or some other feature of spaceflight, that they might be deprioritized for a mission. So right now, there's the Genetic Information Non-Discrimination Act. They're not supposed to be making decisions based on that. And then also, we have very small sample sizes right now. If a scientist publishes a study like that, it might not be statistically relevant to be making decisions off of it. But there's still this concern. And actually, when you move to the commercial spaceflight sector, the reasoning behind missions is different. And so if you're paying for your own ticket, it's up to you to determine whether or not the risk is worth it to you. And so on the commercial side, what I could see being developed is, and this would take a lot more people going into space and collecting a lot more data to get the database that you need for this, but some sort of DNA testing where you get a risk profile for what sort of concerns that you would experience when you go into space, whether or not that's cancer risk or some other unknown factor.
All right, so I don't know why I didn't think of this, but like what you just said made me think of it. Gattaca, right? Basically, that's what you're talking about is anticipated in the film Gattaca. And honestly, I don't know why it would be bad. I mean, it's expensive, it's risky, other people's lives might be at risk. I don't know. I'm just saying, put that out there, like,
Yeah,
you know.
different. It's different when it's a government mission, I think, versus a private mission. If you're paying for your own ticket versus if it's being paid for by taxpayer money. If it's taxpayer money, you probably do want to minimize as many risks as possible and optimize the success of the mission using whatever data you have available. I don't think we're, close to the point though where we could accurately decide not to send somebody on a mission because of their genetic profile. I just don't think we have that data yet.
Yeah. And just to be clear, Gina was passed, I think, in like second Bush administration. George W. Bush. So this is after Gattaca. I never made the connection. I was like, oh, okay, well, maybe some people had watched Gattaca, they're like, oh, we don't want to discriminate against people like Ethan Hawke. He's great, I don't know. So, as you're doing this stuff, and I know that you have like this big tranche of, I know, like they know, everyone knows. I'll put some links I'll put a link to your Google Scholar because all the papers are there. There's a lot of them. As they came out this year, what was the most surprising thing for you out of your results?
One of the things that I want to follow up on, and this would take, collecting samples more frequently after they return. So we collected samples at R+1 one day after return, about a month after they returned, and about 3 months. But one thing I noticed 1 month after they returned was specifically in the gene expression, the single cell PBMC sequencing data that we had, was that we were seeing novel gene expression pathways emerge 1 month after flight that weren't present in R+1 and then went away again at the 3 month time point. So to me, that's indicating there's some sort of recovery response happening when people come back to Earth. And that'll probably be way more dramatic for people who've been up there for a longer period of time, like how Scott Kelly had that really bad skin reaction. And so I think there's a question too, if people go to Mars and they come back, so they're not doing a one-way trip to Mars, or maybe they go to the moon for a while, they're on the station for a while, and they come back to Earth, what is their recovery process going to be when they have to readapt to gravity? So I think there's a really big opportunity there to figure out about readaptation to Earth.
Yeah, that makes sense. It's going to be, the more I think about it, it's going to be a big deal in the coming decade because, we're on this exponential curve of how fast SpaceX is pushing things. And, 10 years from now is going to be a whole different universe. You have a lot more data. So just, I see like some of the stuff is like in Nature Communications, open access, whatnot. What has the peer response been? I'm asking this specifically. I'll just like put it out there. I saw some people were like, "Oh, these look cool, but like, do we really need to like spend money on this area when we have cancer?" Which is like, whatever. Like, it's weird how parochial scientists can get because, people would be like, "Oh, why are you studying fruit flies?" Or whatever. But like, have you gotten any feedback, or has everyone been pretty like supportive or like gotten it?
Well, I think that's an interesting point. So a lot of the funding for the sequencing work of this project actually came from the World Quant Foundation, which is a private foundation. So the vast majority of this, there was some NIH funding, there was some NASA funding, but the vast majority was actually private funding. And I think if NASA and the NIH want to study astronauts and genomic responses of astronauts specifically, they're going to have to put a lot more money into it. We're not seeing that right now. One of the things I'm doing with my lab at the University of Austin is we're going to have a sequencing core here, where the profits of that core are specifically applied to astronaut samples. We need to have a pathway we're learning that's independent of some of these funding organizations to get this work done. But overall, from the scientific community, the response has been really positive. So for the NASA twin study, the omics data from that study was never really accessible in a public database. for, privacy reasons. We know exactly who that individual is. Also, the twin of that individual is a senator. They're very high profile individuals. And so there were some privacy concerns there. For Inspiration 4, since it was a commercial crew, they wanted, for their own mission reasons, they wanted to get their data out there. Their priorities were a little bit different. And we also, there's 4 of them, so you don't know right off the bat who's who. Though I'm sure if you dig around in the data, you can probably figure it out. If you're, a genomics expert. So that data, it's the first publicly available astronaut data. It does have for the raw data, one level of verification that you're with a research organization. So if you go to NASA GeneLab, you'll have to fill out, similarly to dbGaP, you just have to fill out some institutional affiliation information. So just from terms of, this is the first time people can really explore this data, we've had really positive feedback from the community.
Yeah, it seems like some of the papers here, including I think one of the first authors by you, is you're kind of providing resources for other people to analyze the data, right?
Yeah, so I consider myself a methodology expert. I'm not a biologist by training. My undergrad degree was in computer science. My Ph.D. was in genome sciences, specifically on sequencing methodology. So I did a lot of work with Hi-C, with nanopore sequencing, with ChIP-seq, and then some stem cell culture work. But my specialty was never in specific biological mechanisms. So I kind of knew, when I was working on this project, that to really get the most out of this data, I would need to get it in the hands of those experts.
Nice. Well, so one thing that I'm curious about, actually, wait, I gotta say something. I just realized one reason maybe people might be a little bit skeptical recently. Remember last year, my friend Lee Berger, he sent fossils into space, and there was do you remember that?
I don't know about this. No.
You were too busy analyzing your data and working on your papers. So Lee Berger sent some hundreds of thousands of years old fossils into space. It was with I think it was with Virgin. Yeah, it was Virgin Galactic. And it went into space and it landed safely. But there was a 1 week there's a 1 week hate fest. I have to, whether it's justified or not, it was pretty harsh. And they were just saying Lee was being whatever publicity hound and all this stuff. And could be true, could be not. I'm not gonna take a stance on that. I just think maybe because that's basically if you're a space scientist, whatever, you understand space. But if you're a biologist or an archaeologist, it's you don't understand space. You're what are they doing, right? And I just wonder if you guys, if some people just saw that, were oh, is this some sort of vanity thing? But you're talking about people have been doing this sort of research in physiology, development, exercise and motion science, related to astronauts in space for decades, right? You're just applying, genomics is the new thing, and let's do it, right?
Yeah, well, it's not even novel that we're doing genomics assays in space. That's been done on the ISS before. There's a long track record, or at least a developing track record. Maybe long isn't the right word, but a track record of genomic assays. A lot of transcriptomic work being done from space station missions. The novel part of this was that we were able to do it on a human crew with a sample size greater than N of 1.
Well, I mean, what are you thinking? Just I'm just to give you a question. What do you think your sample size in say 10 years is going to be? Is it going to be orders of magnitude greater, multiple fold greater? I think this is probably going to be driven by SpaceX and the private companies, right?
Yeah, no, I think you're right about that. So I think it will be orders of magnitude bigger. It's hard to say exactly because I think there's an issue of scale. How quickly are these commercial missions going to scale? I think that's one of the biggest unknowns. Some of that depends on these new space stations that are being built. For example, Blue Origin is developing a station called Orbital Reef. Axiom Space, they're going to the space station now, but their plan is to build modules off of the ISS, detach it, and become their own free-flying station. VAST is also working on a space station. So there might be a lot more destinations for people to go to. That could drive a lot more people going up there. Also, if Starship, it depends when Starship becomes operational and has life support systems and can start sending crewed missions, because that'll increase the space station, sizes are looking at maybe 4 people at a time. A Starship, at least for like the Dear Moon project, they were looking at having 12 people on a single mission.
Yeah, okay. Okay, that makes sense. Do you anticipate so you're talking about like the time and space, like obviously the amount of radiation, the amount of gravity, like these are parameters we kind of know. I mean this is why you do the experiment, but if you're going to Mars, I mean, is there anything that we wouldn't know from going to the moon? Like in terms of the response, because it's like we know what the moon's gravity is. So like what I'm trying to get at, just for the listener, is like, okay, we know what 1G is, we know what 0.05 Gs are, and if we're seeing some physiological response at 0.5 Gs, we should be able to like interpolate in the middle, right? Like have a general model. So once we get the near Earth stuff under control, do you think that that'll give us a good model for how it's going to be going interplanetary or like across the solar system?
Yeah, I think it depends what your goal is. If you just want to start teasing apart these biological responses, I think the moon is probably the fastest destination to go to. If you do want to start developing colonies independent of Earth, then yeah, you have to start thinking about Mars for that. But if you purely want to know biological responses and biological hazards, the moon, I think, would be the next best place to build like the next generation space laboratory.
Okay, so this is just like a speculative question, but I'm going to ask you: can you imagine a scenario where someone gets CRISPRed as an adult to adapt to space in some way?
Yes. So the lab I did my postdoc in, Chris Mason's lab at Weill Cornell, he has a book where he talks about some of this. So, for example, can you be CRISPRed such that you are more radiation resistant, or that your bones and muscles are stronger so that they don't degrade, as quickly due to the microgravity? I think CRISPRed as an adult is obviously much more difficult than being CRISPRed as an embryo. So I'm not sure where the most logical place to intervene is. Or if you're only, and I mean, that's a big commitment to be CRISPRed in that way. You have to kind of be at the point where you're going to be there for your entire life. Because if you increase your bone and muscle mass and then you come to Earth, maybe there's some interference there and you're not as healthy on Earth as you would have been without those modifications. So that's definitely for a variety of reasons further out, but it might be necessary in the long term.
All right. So I didn't know about this book. I'm gonna just like name check the book. I'll probably put a link to it. It's your PI, your advisor, supervisor for your postdoc. The next 500 years, engineering life to reach new worlds. It was published in 2022, so a couple of years ago. It looks like a very interesting book. It's got some well, it has the George Church blurb, so that's good. Also Manolis Kellis, some other people. So good, right? Did you read the book, or were you? Did you read early drafts of it?
Yeah, I have a copy of it. I have a signed copy from Chris from being in his lab. Yeah, I've read the book. Yeah.
So Eliah, like, what are you looking forward to in the next couple of years? Obviously, your sample sizes are going to get really, really big. You're going to start a course. You're going to start sequencing. And you're looking for people who have projects and other things that maybe they want to use the core for here at University of Austin, in Austin. So I know that's going to be the short term. Like, what other projects and papers are in the pipeline?
Yeah, so one of the things I'm hoping we can do more of is we collect more samples from these crews. There's a huge gap in epigenetics work that's been done in space. We've done a lot of work on transcriptomics, but we don't know a lot about how histone modifications are changing and how that might be influencing gene expression, or about chromatin conformation. And some of this is because you can only draw so much blood from these crews, so you can only perform so many assays. So you have to prioritize data that you've collected in the past, so that you have a bigger sample size to compare to. So like we wanted to compare it to the twin study, so we did a lot of the same assays so that we could have a larger group of gene expression data sets to look at. But as you get larger and larger groups, you can start to diverge from the path and do more, do the next level of analysis. So I'm looking forward to, is if the sample sizes do take off, as I hope they do, being able to perform a wider breadth of assays. The other thing that I'm looking forward to is one of the things that Inspiration 4 demonstrated was that there's new pathways to access spaceflight. So it used to be you always had to go through NASA. If you wanted to go to space, you had to become a NASA astronaut and you had to go through that pipeline. We're seeing these pipelines change. So, like for Inspiration 4, you had one person who bought the whole mission and commissioned all the science that was happening there. With Axiom, you have astronauts who can pay for their mission and scientists who can pay to fly their experiments. And then there's other organizations, the Space Exploration Research Agency, SARA, they're commissioning Blue Origin flights and filling those flights with crews. And so there's a question now of, can we get students and faculty and researchers access to space through one of these novel pipelines? So one of the things is, if you become a NASA astronaut, you have to give up your research agenda and you have to focus on the priorities of that organization. So for scientists, who have their own ideas and want to test their own hypotheses, how can we get them to fly on one of these new pathways that's emerging? So that's one of the things I'm hoping to develop here at UATX, is a pipeline for, if you're a student, if you're a researcher, if you're an entrepreneur, how can we get you and your experiment in space?
So we are in Austin. We've been talking about space, and mentioned SpaceX. Just a random question. Have you talked to Elon at all? I'm just wondering because he's interested in all sorts of, weird, wild things. Well, I have a friend. People in Austin know me. I have a friend, and her postdoc is. I mean, this is openly known. Her postdoc in effective altruism here at UT, and it's a very well funded postdoc, is funded by Elon. So he funds all sorts of things.
I haven't talked to Elon. I think it would be an interesting conversation.
All right. Well, we'll see if we can get that to happen. I do see him at social events every now and then. I have not had a chance to talk to him about anything that is transactional. So I just don't talk to him because you only get like a couple of shots. But maybe we can talk Eliah. Like maybe I can pitch him something at some point.
Yeah, that would be great.
All right. Well, it was great talking to you. I really appreciate you taking time out of your day. It's a very hot day here in Austin today. So, it's great to be inside. We're definitely not doing this outside. And, really also appreciate the guest appearance by your cat.
Yeah, the audio only listeners won't be able to see that. But.
Yeah. The cat's chilling in the background, listening. Because the cat can't hear me, right? So, or can the cat hear? Cat can hear me.
Yeah, and he can.
Okay, yeah, that was great. Yeah. Okay, yeah. So the cat can hear me. So the cat was just chilling back there, listening to what was going on. Anyway, it was great talking to you, and I will see you literally around town.
It's great talking to you.
Embryos have a 30 to 60% difference in the predisposition to severe diseases. With ORCID, parents can identify their embryo at lowest genetic risk rather than just a random outcome. Our genetic calculator can show the impact of embryo selection. Discuss embryo screening and IVF with a genetics expert.
This podcast for kids